Hello everyone, welcome to this online course on material science. I am Dr. Imtiaz Ahmed. This is lecture 16 in module 1. And if you recall, in the last lecture, I discussed the classical model of paramagnetism where we derived the expression for the Langevin model of paramagnetism and then show how the Curie law can be derived from this Langevin model, right? Now, from today, my plan is to discuss the quantum mechanical treatment for paramagnetism, and for that, we need some basic concepts from quantum mechanics. And my plan here is to give you the ideas required to understand the model ahead. So I will be using these two references for a number of lectures to come. So the first one is the Magnetism in Condensed Matter from Stephen Blundell, and then the other one is that there is a nice set of lecture notes on solid state physics, magnetic properties of solids, written by the famous Amos Dresselhaus, right, from MIT. So have a look at these two sources to follow my lectures if needed. But my plan here is to give you most of the things in such a way that you will understand the things to handle the paramagnetic problem in a quantum mechanical approach, right? So let's start discussing about a key point that I mentioned in the discussion of diamagnetic material, right? You remember I said that to observe diamagnetic behavior in a solid, the atoms in the solid should have a closed shell structure, right? It means it should have its outermost shell followed by the 2n square law, right? So let's say we have some maybe a neon, right, which is 10. So we have 1s2, 2s2 and 2p6, right? So the outermost shell has 8 electrons, and that's the second energy level. So 2n square should be 8, right? Because n is equal to 2 in this problem. So those closed shell structure atoms, right, had a nice feature that in their ground state, right, electrons inside a closed shell atoms in its ground state has zero angular momentum, right, orbital angular momentum. If you recall, I mentioned this expression that the angular momentum or the orbital angular momentum is an operator in quantum mechanics, and in the closed shell atom where the ground state is denoted by this zero symbol, right, the zero ket, it kills the state. What it means is that the orbital angular momentum for a closed shell atom is zero. That's the central point I mentioned. But now I need to add some more properties of the closed shell atom, because not only the L, which is the orbital angular momentum, kills the state, it turns out that even the spin angular momentum produces zero, and also the total orbit angular momentum, the total angular momentum denoted by J, is also zero, right? So in a closed shell atom, the orbital angular momentum, the spin angular momentum, and the total angular momentum, all of them have zero value in their ground state of the electron. And that's one important thing, that for diamagnetic material, we always discard about this closed shell atoms, right? And then you will see in the textbook, this condition is usually written as that expectation value of the orbital angular momentum in the ground state, right, is zero. So that's how we usually, this expression is written. And also the spin angular momentum, the expectation value in the ground state is zero, and also the total orbital angular momentum, the total angular momentum, the expectation value is also zero, right? So these are the characteristics for closed shell atom. But now we want to start discussing the paramagnetic behavior of atoms, right? For that, so let me just give you the central rule is that if you want to understand the paramagnetic behavior, the atoms should be partially filled, right? That's one important take-home message, that for partially filled atom, paramagnetic behavior usually dominates. So partially filled atoms. That's a crucial point. And one also should understand is that the behavior of these partially filled atoms and the closed shell atoms are quite different, right? That's why in order to understand the magnetic material in a paramagnetic regime, one needs to understand fairly at a good level these three angular momentums, right? Let me write down on record that these three orbital angular momentum, right? So this is orbital angular momentum. Then we have spin angular momentum. Then we have this J, which is nothing but the sum of the orbital angular momentum plus the spin angular momentum. Every one of those things are operator in quantum mechanics, right? So this is the total orbital angular momentum. The question is that you need to understand fairly well these three angular momentum to understand the behavior of electrons in a partially filled atoms, right? And that's where this collection of angular momentums become really important. So for partially filled atoms. So that's the central message of this lecture, is that it's really hard if you don't understand how you model L, S, and J in quantum mechanics, and then without them you really don't understand how the paramagnetic behavior can be obtained in the quantum mechanical setup, right? So to that approach, my aim is that in lectures to come, I will give you a series of lectures on orbital angular momentum, then spin angular momentum, and then total angular momentum, so that you have enough to understand the paramagnetic behavior from a quantum mechanical setup. And I will give you the set of rules and take them as a rule, and once you understand them and use them in your problem, you will see you will gain more experience, right? So don't worry that I will give you enough so that you will not have any problem understanding a standard textbook on magnetism, where quantum mechanical treatments are widely used to explain the paramagnetic behavior, right? So that's my plan, and I think for this lecture that's about it, and thanks for listening.